So today we're going to be talking about Hardy-Weinberg Equilibrium. This is just a quick way to understand how to work problems like this, since this is a relatively new topic. So some terms you're going to need to know is when we're talking about phenotypic frequency, this is looking at the different phenotypes of the population. When it's really important to know that both homozygous dominant and heterozygous display the same phenotype, while homozygous recessive displays a different phenotype, and so those are what we're going to be separating out. We can also be talking about allelic frequencies, and this is looking at how many dominant alleles are and how many recessive alleles are in a population. Note that according to Hardy-Weinberg Equilibrium, the number of dominant alleles, which is P, plus the number of recessive alleles, which is Q, has to equal 1. And then we also can find genotypic frequencies using Hardy-Weinberg Equilibrium. And this is just saying that you have to determine how many members of a population are homozygous dominant, who are heterozygous, and who are homozygous recessive. So homozygous dominant individuals are P squared. Heterozygous individuals are 2 times P times Q. And homozygous recessive individuals are Q squared. Now again, like I said, with the allelic frequencies, the P's are referring to dominant alleles, and Q's are referring to the recessive allele frequency. So if we're going to work a practice problem, this problem actually comes from the book. It's chapter 18, number 29. We have full color domestic cats are going to be dominant over dilute color domestic cats, and we have a population of size 325. Out of that population, 194 of them are full colored, and 131 of them are dilute color. So what we're going to work through is how to find the phenotypic frequency of this population, the allelic frequency of this population, and the genotypic frequency of this population. So this first one, if we're looking at the phenotypic frequency, like I said earlier, we're looking at strictly, is it full color or is it dilute color? Because those are the two phenotypes that we have. And so this is really easy to do with this setup, how this problem is presented. So we know that full color, there are 194 cats. There are 131 cats that are dilute colored, and the total population is 325. So to find the phenotypic frequency for full color, we would say 194, which is the number of full color cats in the population, divided by the overall size of the population, which is 325. This gives you 0.596 or 60%. Then we do the same thing for dilute color. The dilute color, there are 131 individuals out of a total population of 325, which gives you 0.403 or about 40%. This is basically how we figure out the phenotypic frequency. It's pretty straightforward. Allelic frequency. So now what we're going to be doing is counting the number of alleles that are present. And so with the full color domestic cats, what we need to know is that, when we're dealing with dilute colored, since dilute is the recessive allele, if we have the number of dilute colors, this is homozygous recessive. And so this is what we're going to start with to figure out the allelic frequencies. We know that 131 out of the total population are dilute colors, and so we say 131 divided by 325. That gives you 0.403. That is our Q squared value. And so to find Q, which is the allelic frequency, or how many little d's there are in the population, we just take the square root of that number, and that gives us 0.635. Now to find P, we have to go back to the Hardy-Weinberg equilibrium equations, and we say, okay, well, we know what Q is. We know the equation is P plus Q equals 1. And so then we just solve for P, and we find out that P here equals 0.365. What this tells us is that there are, out of all the population, there are 36.5% are the big D alleles. Finally, we're going to pull all of what we found together to figure out the genotypic frequency. So looking at this, what we're looking for are to determine the number of individuals that are homozygous dominant, which ones are heterozygous, and which ones are homozygous recessive. So here we know homozygous dominant individuals are going to be p squared. So we take the p that we found from the allelic frequencies, and so p here equals 0.365. We're going to square that value and then times it. And so p squared gives you 0.133. Now, we need to figure out how many people are in the overall population are homozygous dominant, and so we take this frequency and multiply it by the overall population. So 3 times 0.133 times 325, and that gives you 43 full-colored cats. Now, to find out how many are heterozygous, which are big D, little d, that is going to be 2 times P times Q. And so we say 2 times 0.365 times 0.635 gives you 0.463. And so we're going to take that frequency and times it by the overall population, which is 325. And that gives you 151 full-colored cats. So what we notice here are that 43 plus 151 gives us the 194, which is what we were told in the problem. However, only 43 of them are homozygous dominant. And then homozygous recessive is kind of redundant because it gives us this earlier, but we know we can calculate it again just to make sure we're right. We take q squared, which is 0.635, square it, which gives you 0.403. Then we times it by 325, and that gives you 131 dilute cats. Now, just to make sure your math is correct, we need to use the Hardy-Weinberg Equilibrium equation. And so we say p squared, which was the 0.0133, plus 2pq, which is the 0.463, plus q squared, which is 0.403. We add those up, and those should equal 1. Now, in this case, we get 0.999, and that's because rounding errors and stuff like that, but it's close enough to 1 to know that we did the problem correctly. Problems like this could be presented in a multitude of different ways, but this is just one problem that we're all familiar with from the homework. And so if you have any other questions, make sure to ask Professor Grunda, or you can ask me. Thanks so much.